So, dear students, today's concept is how to calculate crystal field stabilization energy and also pairing energy. Before we are entering into this concept, you have to know what is a spectrochemical series, which is nothing but the strength of ligands series. So, the spectrochemical series is spectrochemical series, which gives us spectrochemical series. Which gives us the strength of the ligands. The series order is I minus is less than Br minus is less than Cl minus is less than NO3 minus is less than F minus is less than OH minus is less than oxalate ion OX2 minus is less than water neutral ligand is less than up to water. These are all weak field ligands. These are all weak field ligands. Hot water pyridine is equal to NH3 is less than ethylene diamide is less than ortho is less than NO2 minus is less than Cn minus is less than CO. So these are all strong field ligands. Strong field ligands. First, you have to know, before entering into the calculation of crystal field stabilization energy and pairing energy, you have to know the spectrochemical series and also the splitting of d orbitals in octahedral complex as well as in tetrahedral complex. So you have to know which ligand is weak field ligand and also which ligand is a strong field ligand. According to spectrochemical series, there are weak field ligands and strong field ligands are indicated. And how can we calculate the crystal field stabilization energy for octahedral complexes? So we have two types of ligands, weak field ligand and strong field ligand. We have to calculate the crystal field theory. Crystal field stabilization energy of octahedral complexes like this. Cfse of octahedral complexes is equal to minus 0.4 N-T2Z triply generated plus 0.6 N easy plus number of pairing electrons. The crystal field stabilization energy of octahedral complexes represented by delta O. So let us see. If the central metal atom has a D1 configuration, D1 configuration, D1 configuration. So first we have to write configuration T2Z easy when weak field ligand is present, the electronic configuration weak field ligand octahedral complex and Cfse of octahedral. If there is strong field ligand is present along around the central atom, according to the configuration, we can calculate the Cfse of delta O. So first one is D1 configuration, T2Z, and we see dxy, dyz, dzx orbitals are present in T2Z. In each set, dx square minus y square and dz square orbitals are there. For D1 configuration, electron enters into T2Z level and the configuration is T2G1 EG0 in the presence of weak field ligand as well as in the presence of strong field ligand. The configuration is the same. T2G1 EG0. How can we calculate delta O? So T2Z1 minus 0.4, only one electron, n is equal to 1. T2Z contains only one electron, plus there is no easy electrons and there is no paired electrons. Therefore, we get minus 0.4 dq integral. So in this concept also, in this in the presence of strong field ligand also, we have minus 0.4 dq. So what happens if the central metal atom has a D2 configuration? So electron enters into T2Z level. The electron configuration is T2G2 EG0. Then minus 0.4 into 2. Remaining easy electrons are 0 and there is no paired electrons. That is equal to minus 0.8 dq. In the case of strong field ligand also, there is T2G2 and EG0 electron configuration. Here also 0.8 dq. So in the case of D3 configuration, In the case of D3 configuration, electronic configuration is T2G3 EZ0, weak field ligand delta 1 is equal to minus 0.4 into 3, that is equal to minus 1.2 becquerel. So the same configuration in the presence of strong field ligand also, T2G3 is 0, T2G3 is 0, delta O is also minus 1.2 becquerel. Next, from D4 configuration, a D4 configuration, if weak field ligand is there, the electronic configuration is T2G3 and EZ1 minus 0.4 into 3 plus 0.6 into 1, that is equal to minus 0.6 becquerel. This is in the presence of weak field ligand electronic configuration. But in the presence of a strong field ligand, T2Z4 and EZ0, after filling of all T2G orbitals, then electron enters into EZ level in the presence of a strong field ligand. So we get delta O is like this. Minus 0.4 into 4, that is equal to minus 1.6 becquerel. So here, let us see the configuration. T2Z4, 1 pair and 2 unpaired electrons. So 1.6 plus P, there is 1 pair of electrons, the pairing energy P is added. Then we get, if the strong field ligand is present in the complex compound around the central atom, the Cfse value is, if the central atom has D4 configuration, then the delta O of that central metal atom is minus 1.6 plus P, and that is P is pairing energy, which is nothing but the energy required to pair 2 electrons against electron-electron repulsions in the same orbital. Pairing energy, which is nothing but the energy required to pair 2 electrons against electron-electron repulsions in the same orbital. Next is a D5 configuration. So in the case of a weak field ligand, the configuration is like this: T2G3 and EZ2. So delta O0 is equal to 0.0. Calculate minus 0.4 into 3 plus 0.6 into 2. There is no paired electrons. 1.2 minus plus 1.2. That is 0.0 becquerel. 0.0 becquerel. Becquerel. So what happens in the case of a strong field ligand in which the central atom has D5 configuration? T2Z5. T2Z5 means which contains 2 pairs of electrons and one unpaired electron. Easy 0. Easy 0. No electrons in easy orbitals, dx square minus y square and dz square orbitals. So then we have to calculate the Cfse of octahedral complex like this: 0.4 into 5 plus 0, that is equal to minus 2.0. There are two pairs of electrons, so 2.0 plus 2p is the crystal field stabilization. So we have to calculate these Cfse values based on configuration up to D10 configuration. So you have to know what is the pairing energy. Pairing energy P is nothing but pairing energy, which is represented by P, which is nothing but the energy required to pair. The energy required to pair two electrons against electron repulsions. Electron repulsions in the same orbital. In the same orbital. The same orbital. This is a pairing energy. And you have to know one more relation between the Cfses of delta O and delta T. This is also important. Relation between delta O and delta T. Cfse of octahedral complexes and Cfse of tetrahedral complexes. Most important relation. Delta T is equal to 4/9 delta O, or delta O is equal to 9/4 delta T. 9/4 delta T. So this is today's concept. Thank you very much.